The beginning of matter. What came before the atom? What existed before the first atoms? Before protons and neutrons? Before even the concept of particles we know today? To answer that, we must go back in time farther than stars, galaxies, or even hydrogen. We must return to the very first microsecond after the Big Bang. At that moment, the universe was a seething soup of unimaginable temperature and density, a state so extreme that the matter as we know it could not exist. Approximately 1/1,000,000th of a second, 10 seconds after the Big Bang, the universe reached temperatures of several trillion Kelvin, conditions hot enough to melt protons and neutrons into their most fundamental building blocks, quarks and gluons. In this era, no atoms had yet formed, no stable particles existed, only a dense, energetic medium called the Quark-Gluon Plasma, or QGP. Today, we're going to take a journey back in time to understand this primordial state of matter. What is it? How do we know it existed? And most remarkably, how have scientists managed to recreate this moment of cosmic history inside laboratories on Earth? This is not just a story of the distant past. Studying the Quark-Gluon Plasma offers a powerful lens into the forces and particles that shape our universe today. It connects us to the very fabric of the cosmos and to the fundamental question, where does matter come from? In this episode, we will explore what quarks and gluons really are, how they combine to form the particles of matter, and how under extreme heat and pressure they break free from their bonds to create a new phase of matter. This is the story of the first moment when the universe became real. Are you ready to step into a trillion-degree fireball and witness the universe in its infancy? Let's begin. What are quarks and gluons? Understanding the building blocks of matter. Before we dive deeper into the plasma state, we need to understand the fundamental ingredients, quarks and gluons. Quarks are the most basic known constituents of matter. They are elementary particles, meaning they are not made of anything smaller that we know of. Quarks come in 6 types, or flavors: up, down, charm, strange, top, and bottom. But in the everyday matter around us, such as the atoms in your body, we mostly find just up and down quarks. Protons and neutrons, which make up atomic nuclei, are not indivisible. They are made of quarks. For example, a proton is made of 2 up quarks and 1 down quark, while a neutron is made of 1 up quark and 2 down quarks. These quarks are held tightly together by a fundamental force known as the strong nuclear force. And that's where gluons come in. Gluons are the particles that carry the strong force, just like photons carry the electromagnetic force. In simple terms, gluons glue quarks together, hence their name. This interaction between quarks and gluons is described by a branch of physics called quantum chromodynamics, QCD. QCD is a central part of the standard model of particle physics, which is the most accurate theory we have for explaining how particles and forces interact. In QCD, quarks have a property called color charge, not actual color, but an abstract quality similar to electric charge. Gluons constantly exchange these color charges between quarks, binding them together so strongly that we can never isolate a single quark under normal conditions. This is known as quark confinement. But under extreme conditions like those found just moments after the Big Bang or in high-energy particle collisions, we can overcome this confinement. That's when the Quark-Gluon Plasma forms, a state where quarks and gluons roam freely, no longer locked inside protons or neutrons. So why is this important? Because understanding quarks and gluons and the rules they follow helps us answer some of the deepest questions in science. How does matter hold together? Why is the universe stable? And what happens when we tear it apart at the most fundamental level? In the next section, we'll explore exactly what Quark-Gluon Plasma is and how it differs from the forms of matter we experience every day. What is Quark-Gluon Plasma? The first state of matter so far. We've talked about quarks and gluons, the building blocks of matter and the forces that hold them together. But what happens when we go back in time to the very first microseconds after the Big Bang, when the universe was hotter and denser than anything we can imagine? That's when Quark-Gluon Plasma or QGP comes into play. Quark-Gluon Plasma is a unique state of matter, in which quarks and gluons are no longer confined inside protons and neutrons. Instead, they move freely in a hot, dense soup of particles. This plasma existed only within the first millionth of a second after the Big Bang, at a temperature of around 2 to 4 trillion degrees Kelvin, more than 100,000 times hotter than the center of the sun. To put it into perspective, in our everyday world, we observe matter in solid, liquid, gas, and sometimes plasma states. Plasma, like the kind you find in lightning or the sun, is made up of ionized atoms. But Quark-Gluon Plasma goes even deeper. It has not just atoms falling apart into electrons and nuclei. It has nuclei themselves dissolving into the quarks and gluons that make them up. At these extreme temperatures and densities, the strong nuclear force is effectively weakened. This allows quarks and gluons to deconfine. They are no longer trapped inside hadrons, a term for particles like protons and neutrons. The resulting mixture behaves like an ultra-hot liquid, where particles interact so frequently that they flow collectively, almost like water. In fact, one of the most surprising findings from recent experiments is that QGP behaves more like a perfect fluid than a gas. It has very low viscosity, meaning it can flow with almost no resistance. This makes it one of the most perfect liquids ever observed in nature. This state is incredibly short-lived. In both the early universe and in modern laboratory experiments, QGP lasts for only a tiny fraction of a second, around 10 seconds, before cooling and condensing into hadrons again. But during that brief window, it gives us a rare glimpse into the birth conditions of the cosmos. Scientists use sophisticated simulations and theoretical models to understand how quarks and gluons behave in the state. These insights help physicists refine quantum chromodynamics and test its predictions under extreme conditions we simply cannot reproduce in any other way. In the next section, we'll rewind the cosmic clock even further to see how Quark-Gluon Plasma naturally occurred in the earliest moments of the universe, just after the Big Bang. The early universe and the existence of Quark-Gluon Plasma. To truly grasp the significance of Quark-Gluon Plasma, we need to go back to the very birth of our universe, specifically to the window of time between 10 and 10 seconds after the Big Bang. During this fleeting moment, the universe was unimaginably hot and dense, a cauldron of raw energy and fundamental particles. The temperature of the universe at this stage was estimated to be between 2 to 4 trillion Kelvin. At such extreme conditions, protons and neutrons couldn't yet exist. The thermal energy was so intense that any attempt for quarks to bind together into hadrons was instantly disrupted. Instead, quarks and gluons floated freely, unconfined, creating what we now understand as the Quark-Gluon Plasma. Imagine the early universe as a cosmic soup, not made of atoms or even nuclei, but of the most basic constituents of matter swirling around in a seething storm of energy. There was no structure, no stars, no galaxies, not even simple hydrogen atoms. The universe, at that point, was a primordial fluid, dominated entirely by this quark-gluon mixture. This phase was critical. It marked the transition from a state governed purely by energy and fundamental forces to one where particles began forming the building blocks of matter. After just a few microseconds, as the universe continued to expand, it cooled down just enough for quarks to start combining into protons and neutrons. These would later form atomic nuclei and eventually the atoms that make up everything we see today. Why does this matter? Because by studying the conditions that allowed Quark-Gluon Plasma to exist, we gain insights into the symmetry of forces in the early universe, the origin of mass and the formation of matter, the timing and mechanism of the transition from QGP to hadronic matter. In essence, the brief appearance of QGP was the first chemical fingerprint of our cosmos. It tells us how the early universe evolved from pure energy into particles, and then into complex structures like galaxies and planets. But how do we know this? And is it even possible to recreate such an exotic condition on Earth? That is exactly what we'll explore in the next section. where humans have used some of the most powerful machines ever built to recreate the first moments of the universe in controlled laboratory settings. How do humans recreate Quark-Gluon Plasma on Earth? Recreating the conditions of the early universe on Earth might sound like the stuff of science fiction, but thanks to decades of innovation in particle physics, scientists have indeed managed to bring back the first microseconds of the cosmos right inside laboratory settings. To do this, researchers use heavy ion colliders, massive machines that accelerate atomic nuclei to speeds near that of light and smash them together. When such ions collide at ultra-relativistic speeds, they momentarily generate the extreme temperatures and energy densities required to melt protons and neutrons back into their constituent quarks and gluons. There are two major facilities in the world where this has been achieved: RHIC, Relativistic Heavy Ion Collider at Brookhaven National Laboratory in the United States, LHC Large Hadron Collider, specifically the ALICE experiment at CERN in Switzerland and France. Let's look briefly at how these colliders work. Scientists begin with heavy ions like goldo at RHIC or lead Pb at LHC. These ions are accelerated to 99.999% the speed of light. Then they are made to collide head-on inside massive detectors equipped with advanced sensor arrays. In the brief aftermath of the collision, lasting only around 10 seconds, conditions resemble those of the early universe. The temperature can soar above 4 trillion Kelvin, high enough to dissolve hadrons into free quarks and gluons. At this stage, a quark-gluon plasma forms a hot, dense fireball of unbound quarks and gluons. This state is fleeting. The plasma quickly cools and transitions back into normal matter. But in those infinitesimal moments, detectors record data about particle tracks, energy flow, and angular distribution, which scientists analyze to confirm the presence of QGP. Creating QGP in this way is not just about verifying theoretical physics. It also allows scientists to study how matter behaved at the very beginning of time, long before atoms, stars, or even light existed. Through these experiments, we don't just simulate the Big Bang, we revisit it using advanced technology as a time machine. And what scientists have discovered in these collisions has redefined our understanding of matter. Under extreme conditions, in the next section, we'll dive deeper into the specific results from these groundbreaking experiments, starting with RHIC, where physicists first claimed, "We have created the hottest matter in the universe." What did we discover at RHIC? The first evidence of Quark-Gluon Plasma, the relativistic heavy ion collider RHIC, located at Brookhaven National Laboratory in New York, was the first facility in the world specifically designed to study the Quark-Gluon Plasma. Since its operation began in 2000, RHIC has provided some of the most compelling experimental evidence, confirming the existence of this primordial state of matter. In its early experiments, RHIC smashed together heavy gold nuclei O+O at nearly the speed of light. These collisions produced energy densities over 10 GeV and temperatures exceeding 4 trillion Kelvin, recreating the same conditions that existed just microseconds after the Big Bang. But what exactly did scientists observe in these collisions that proved the creation of QGP? One of the most surprising findings was that the Quark-Gluon Plasma does not behave like an ideal gas, as many had expected. Instead, it acts more like a strongly coupled liquid, with nearly zero viscosity and near-perfect fluid. This property was so unexpected that researchers coined the term as QGP, or strongly coupled Quark-Gluon Plasma. One of the hallmark signatures of QGP at RHIC was the phenomenon called jet quenching. In high-energy collisions, partons, quarks, or gluons typically produce narrow jets of particles. But in the dense medium of QGP, these jets are suppressed or entirely quenched, meaning the particles lose energy as they move through the plasma. This is like trying to shoot a bullet through a thick liquid. Instead of air, it gets slowed down or completely absorbed. Jet quenching at RHIC was not only detected, but measured with precision. By comparing proton-proton collisions with gold-gold collisions, researchers observed a significant suppression in high-energy jets in the latter, indicating that a dense, interactive medium QGP was indeed present. In 2005, the RHIC team made a bold announcement that echoed through the global physics community: "We have created the hottest matter in the universe." This was no exaggeration. The matter formed in RHIC existed for only a few femtoseconds, 10 seconds. But during the time, it reached energy densities and fluid dynamics never before seen. Moreover, this state of matter displayed collective flow patterns, where particles moved in a coordinated manner, further confirming the strongly interacting nature of the plasma. These experiments were groundbreaking for several reasons. They confirmed theoretical predictions from quantum chromodynamics, QCD, about matter at high temperatures and densities. They introduced a new paradigm. Instead of thinking of QGP as a gas of free quarks and gluons, physicists began to see it as a perfect liquid, possibly the most perfect ever observed in nature. They demonstrated the power of ultra-relativistic heavy ion physics as a tool to explore the fundamental laws of nature under extreme conditions. In short, RHIC gave humanity its first experimental glimpse into the very beginning of the universe atom, before atoms, stars, or galaxies existed. In the next part, we'll turn our attention to Europe, to the ALICE experiment at the Large Hadron Collider at CERN, where scientists pushed these discoveries even further by colliding heavier ions at even higher energies. ALICE at CERN smashing the universe even harder. If RHIC opened the door to the early universe, then CERN's Large Hadron Collider LHC blasted it wide open. At the heart of this monumental effort is the ALICE experiment, short for Large Hadron Collider experiment, which was specially designed to study the Quark-Gluon Plasma under conditions even more extreme than those achieved at RHIC. ALICE began taking data in 2010 using lead PB plus PB collisions at unprecedented energies, up to 5.0 to 10 per nucleon pair, an order of magnitude higher than RHIC. These collisions recreated temperatures over 5.5 trillion Kelvin, conditions that likely only existed less than a microsecond after the Big Bang. So, what did ALICE discover? One of the most astonishing confirmations was that Quark-Gluon Plasma not only exists, but behaves like an almost perfect liquid, just as seen in RHIC, but under even more extreme conditions. This behavior was measured through a property called the shear viscosity to entropy density ratio, known as eta thus. The ALICE results showed that the QGP had an eta that's very close to the theoretical minimum predicted by string theory-based models, specifically the ADS-CFT correspondence, which describes strongly coupled quantum field theories. This means that QGP flows almost without resistance, like superfluid helium, but billions of times hotter and denser. ALICE also observed a phenomenon called elliptic flow, a clear indication that the QGP responds to the geometry of the collision. In non-central collisions, the overlapping region of the two lead ions is shaped like an almond. If QGP were just a weakly interacting gas, it wouldn't show much directional preference. But instead, the produced particles showed a strong azimuthal anisotropy, meaning they flowed preferentially in the plane of the collision. This flow is a hallmark of collective behavior and supports the idea that QGP is a strongly interacting liquid. Another major finding at ALICE was the suppression of heavy quarks. Particles like charm and bottom quarks were found to lose a significant amount of energy as they traveled through the plasma. This is surprising because heavy quarks, due to their mass, were expected to punch through the plasma more easily. Instead, their suppression revealed just how dense and interactive the QGP really is. Perhaps one of the most intriguing discoveries at ALICE is that the QGP appears to be extremely short-lived, existing for only about 10 seconds. But in that blink of an eye, it reshapes the entire environment. It's like a flash of lightning that instantly boils a lake. So, what tools made these observations possible? ALICE uses a wide array of highly advanced detectors, such as the Time Projection Chamber (TPC), which tracks charged particles in 3 dimensions with extreme precision. The electromagnetic calorimeter, used to measure the energy of photons and electrons. The muon spectrometer, designed to detect muons, which are key signatures of heavy quark decays. These instruments collect data from millions of collisions per second, and the amount of information is staggering. To process and analyze this data, researchers use supercomputers and advanced AI algorithms, including machine learning models trained to identify specific particle signatures in the debris of collisions. What makes ALICE so critical to modern physics is not just its ability to confirm what RHIC observed, but its ability to test QCD at new frontiers where the predictions of standard models break down and new physics may emerge. Through these high-energy lead-ion collisions, ALICE gives us an unprecedented laboratory to explore the laws of nature at their limits, pushing us closer to understanding the first microseconds of existence. Why Quark-Gluon Plasma matters. Unlocking the secrets of the early universe. Now that we've seen how scientists recreate the Quark-Gluon Plasma QGP in high-energy collisions, one might ask, why go to such extremes? Why spend decades, billions of dollars, and build machines the size of cities just to study a state of matter that existed for only a fraction of a second after the Big Bang? The answer is simple yet profound. QGP is the closest thing we have to a time machine. It allows us to peer back into the earliest moments of the universe, long before galaxies, stars, or atoms even existed. At its core, the study of QGP helps us answer one of the oldest questions in science. Where does matter come from? Let's break down the major reasons why QGP is scientifically important. 1. It reveals the behavior of the strong force at extreme conditions in the standard model of particle physics. The strong nuclear force described by quantum chromodynamics QCD is responsible for binding quarks together to form protons and neutrons. But QCD becomes nearly impossible to study using traditional methods at extremely high temperatures and densities. By creating QGP in the lab, scientists can test QCD in the non-perturbative regime, where calculations become so complex that numerical simulations like lattice QCD are required. These tests confirm or challenge the predictions of QCD, deepening our understanding of the universe's fundamental forces. 2. It gives insight into the birth of nuclei and atoms. Before protons and neutrons formed, the universe was a boiling soup of free quarks and gluons. The transition from this plasma to hadrons, called the QCD phase transition, is a key event in cosmic history. Understanding how and when this happened gives us clues about how the first atomic nuclei formed and why matter dominates over antimatter in the universe. 3. It helps explain cosmic uniformity and structure. QGP research feeds directly into cosmological models. The behavior of matter in the early universe impacts the cosmic microwave background radiation, the distribution of galaxies, and even dark matter theories. Small fluctuations in the QGP may have seeded the large-scale structure of the cosmos. 4. It tests the limits of theories beyond the standard model. Studying QGP also opens the door to new physics. For example, the nearly perfect fluid behavior of QGP challenges expectations and connects to theoretical frameworks like ADS, CFT duality, a concept from string theory that suggests a deep relationship between gravity and quantum field theory. Furthermore, heavy ion collision experiments allow physicists to look for exotic states of matter or symmetry, violations that could point to physics beyond the standard model, including explanations for dark matter, the matter-antimatter imbalance, and the unification of forces. 5. It creates extreme conditions not found elsewhere. In some ways, QGP research is like astrophysics in reverse. Instead of waiting for cosmic events to happen, we create our own mini Big Bangs and watch what happens under conditions similar to neutron-star mergers, supernova cores, or even hypothetical quark stars. It has this power to recreate and control the early universe, and a lab that makes QGP research not just fascinating but essential to our understanding of reality. Unanswered questions and ongoing challenges in Quark-Gluon Plasma research. Despite the impressive achievements in recreating and analyzing the Quark-Gluon Plasma QGP, this field still holds many unanswered questions. Scientists are far from having a complete picture, and ongoing research continues to push the boundaries of both experimental and theoretical physics. Let's take a look at some of the most pressing open problems in QGP research. 1. How does QGP freeze out into matter? One of the biggest mysteries is how exactly the QGP transitions into hadrons, particles like protons and neutrons, as the universe expands and cools. This process, often referred to as the hadronization mechanism, involves complex dynamics. There are two competing scenarios: sudden freeze-out, where quarks and gluons rapidly bind into hadrons; gradual transition, where particles emerge over a range of energy densities and time scales. Understanding this process would clarify how the structure of matter as we know it, nuclei, atoms, molecules, first emerged. 2. Are there natural QGPs in the universe today? While QGP primarily existed in the early universe, physicists suspect it might still occur naturally in the cosmos under extreme conditions. For instance, the cores of neutron stars or during neutron-star mergers might reach densities and temperatures high enough to produce a QGP-like phase. In fact, some theoretical models suggest the existence of quark stars' entire stellar remnants made of deconfined quarks. However, no such object has been conclusively detected, and confirming their existence remains one of the frontiers in astrophysics. 3. What role do strange quarks play in QGP? A particularly interesting line of research involves strangeness enhancement, the overproduction of strange quarks in QGP compared to regular hadronic matter. This phenomenon was one of the first proposed experimental signatures of QGP and has been observed in collisions at RHIC and the LHC. The behavior of strange quarks, and possibly even charm or bottom quarks, within the plasma can help distinguish between different QCD models and tell us more about the internal structure of QGP. 4. What is the exact nature of the QCD phase transition? Does the transition from QGP to hadronic matter resemble boiling water, a first-order phase transition? Or is it more like melting ice, gradually a crossover transition? Lattice QCD simulations suggest that for zero baryon density, as in the early universe, the transition is a smooth crossover. But at high baryon densities, as may occur in neutron stars, it might become a first-order phase transition. This leads to the possibility of a QCD critical point, a unique set of conditions where the transition type changes. Detecting this critical point is one of the major goals of upcoming experiments, including the beam energy scan to program at RHIC. 5. Can QGP help solve the matter-antimatter asymmetry problem? One of the biggest puzzles in cosmology is why the observable universe is made almost entirely of matter, with hardly any antimatter. In theory, the Big Bang should have produced equal amounts of both. Could the behavior of QGP in the early universe have created a tiny asymmetry? Some models suggest that during the QGP to hadron transition, certain conditions could have led to CP violation, a difference in behavior between matter and antimatter. This is still speculative, but understanding QGP better might provide clues. 6. Are there other exotic phases of quark matter? Beyond QGP, physicists are also searching for other possible phases of matter under extreme conditions. These include color superconductors, where quarks pair up like electrons in superconductors; quark-ionic matter, a hypothetical state predicted at high densities and moderate temperatures; quark-gluon glass, a state where gluons dominate and behave like a saturated field rather than as individual particles. These exotic phases could expand our understanding of QCD and the behavior of matter in extreme environments. In short, the story of QGP is far from complete. Every question answered seems to open up new questions. In the next section, we'll look at the future of QGP research. What new experiments are coming? What upgrades are underway? And how we're preparing to probe even deeper into the first microseconds of the universe. The future of Quark-Gluon Plasma research as we've seen. The discovery and study of the Quark-Gluon Plasma QGP has opened a new window into the birth of our universe. But the journey is far from over. The next generation of research promises to probe even deeper into this exotic state of matter, using advanced detectors, more powerful colliders, and innovative analysis techniques. Here's a look at what lies ahead in the quest to understand QGP and the fundamental laws of nature. 1. RHIC's major upgrade, the Sphinx Experiment 2023 to 2026. The Relativistic Heavy Ion Collider, or RHIC, at Brookhaven National Laboratory is undergoing a significant upgrade with the construction of Sphinx, a next-generation detector, specifically designed to explore the properties of QGP with unprecedented precision, focus, study. The QGP's viscosity, energy loss mechanisms, and heavy quark behavior capabilities improve tracking, calorimetry, and jet resolution. Goal: better understand how QGP behaves like a near-perfect liquid and test QCD predictions under varying conditions. With Sphinx, researchers hope to answer some of the unresolved questions we discussed earlier, such as the nature of QGP freeze-out, energy loss patterns in jet quenching, and the role of heavy quarks in plasma dynamics. 2. The Future Circular Collider FCC, CERN's ambitious plan. CERN is already looking beyond the LHC. The proposed Future Circular Collider FCC is a massive scientific project aiming to build a particle accelerator up to 100 kilometers in circumference, nearly 4 times the size of the LHC. Energy scale: up to 100 teraelectron volts for proton-proton collisions. QGP research, FCC, would provide heavy ion collisions at significantly higher energies, creating even hotter and denser QGP. Objective: explore QCD under extreme conditions and possibly reach new phases of quark matter. If realized, the FCC could take our understanding of QGP to an entirely new level and allow us to simulate conditions even closer to the first instance of the universe. 3. Exploring the QCD critical point, beam energy scan to RHIC. Another key effort is the beam energy scan to program at RHIC. This experiment scans through a wide range of collision energies to locate the QCD critical point, the hypothetical boundary between different types of phase transitions in quark matter. Technique: varying the energy of gold ion collisions from 3 GeV to 20 GeV per nucleon pair. Goal: identify fluctuations in particle production and correlations that signal a critical point. If discovered, the QCD critical point would be one of the most significant findings in particle physics since the Higgs boson. It would confirm a major feature predicted by QCD and help map the full phase diagram of nuclear matter. 4. Precision computing, AI and quantum simulation. The sheer complexity of QGP requires more than just powerful detectors. It also demands advanced data analysis tools. Artificial intelligence, AI, and machine learning, ML, now used to sift through millions of collision events per second, recognizing patterns that might escape human eyes. Quantum computing, although still in its infancy, quantum simulation holds promise for modeling QCD and particle interactions that are currently intractable with classical computers. These technologies are enabling physicists to simulate QGP behavior at the microscopic level, providing deeper insight into how quarks and gluons interact over time and scale. 5. Global collaboration and open science. QGP research is a truly global effort, uniting physicists from the United States, Europe, Asia, and beyond. With open access to data and cross-collaboration among major laboratories like CERN, Brookhaven, GSI Germany, and RHIC in Japan, the field continues to grow rapidly. New international programs such as FAI, or Facility for Antiproton and Ion Research in Germany, are also poised to contribute fresh data and perspectives on heavy ion collisions and QCD phenomena. Look ahead. As we look to the future, the study of Quark-Gluon Plasma stands at the frontier of both cosmology and quantum physics. With the next generation of accelerators, detectors, and computational tools, Scientists are well positioned to answer fundamental questions about the nature of matter, the evolution of the early universe, and the limits of our current physical theories. Now that we have traveled through the birth of the universe, unraveled the mysteries of quarks and gluons, and explored how modern science recreates the most extreme conditions imaginable, it's time to reflect on what all of this means. 1. Quark-Gluon Plasma. The first memory of the universe. Quark-Gluon Plasma is more than just a scientific curiosity. It is the first known state of matter in the universe. It existed long before atoms, stars, or galaxies, before anything we know took shape. For a fleeting moment, everything was a boiling soup of fundamental particles, moving freely in a fireball hotter than any star. Understanding this state is like holding the key to a cosmic time machine. When we recreate QGP in laboratories, we are essentially turning back the clock to the first microsecond after the Big Bang. We are witnessing the same processes that gave birth to all structure and matter in the universe too. Humanity's achievement in the lab, the fact that humans have succeeded in reproducing this state, that we can create a piece of the early universe on Earth, is one of the greatest achievements of modern science. It is a testament to human curiosity, ingenuity, and cooperation across continents and generations. Through powerful machines like the LHC and RHIC, we have opened a new chapter in high-energy physics. We are not only testing our theories but also rewriting them, refining our understanding of the strong force, and pushing the limits of the standard model. 3. Big questions still remain, but many questions are still unanswered. What exactly triggers the transformation from QGP to normal matter? Can we detect QGP in natural environments, like inside neutron stars? Is there an even more exotic phase of matter waiting to be discovered, such as quark-gluon glass or color superconductors? Each experiment leads to more questions, and that is the beauty of science. The deeper we look, the more mysterious and fascinating the universe becomes. 4. Why it matters to everyone. You might be wondering, why should any of this matter to me? Because QGP research helps us understand the fundamental building blocks of reality. It helps answer some of the biggest questions humanity has ever asked. Where did we come from? What is everything made of? How did the universe begin? And beyond that, the technologies developed for particle physics, from superconducting magnets to data processing. Algorithms have already impacted fields like medicine, computing, and energy research. 5. Be part of the cosmic journey. So if you've enjoyed this journey into the heart of the early universe, here's what you can do. Like this video to support our work. Share it with friends who love science and space. Subscribe to our channel, Astronomical Library, for more deep dives into cosmic mysteries. And leave a comment below. What do you think about the idea that the universe began as a superheated quark soup? Do you believe there's even more to discover beyond the standard model? Your engagement helps us reach more curious minds like yours, and inspires us to keep exploring the unknown. Until next time, keep looking up, stay curious, and never stop asking questions. Because the universe is not just out there, it's within us, in every atom, every particle, every heartbeat. See you in the next video.